Okay, welcome back, and now we're going to solve this problem which is related to the work done by the pressure. So again, I want you to recall the general procedure. I hope you always keep one of these pages when you solve the problems. So basically, let's go very quick. Step 0, you need to read the problem and do some type of figure summarizing all the input and what you need to calculate. Then step number 1 sometimes is a bit redundant from step 0, but anyway, it's important because you're going to use that figure in order to write down the equations, which is in step 2. You write down the main solving equation and you try to solve. If you see you don't have enough information, then you need to go to step 3, which is to find the additional equations or information. And once you have all the information to solve, then you can go to step 4. Okay, so let's get started. So this problem over here, let me read the problem statement. What do they say? A frictionless piston cylinder device. So I would do this. You see, I read one sentence, not even the first 1, 2, 3, 4 words, and I stop. Okay? And I keep, and I write down the information. Contains 5 kilograms of nitrogen. 5 kilograms of nitrogen at 100 kilopascals. So you can say here at step 1, you know that the initial pressure is 100 kilopascals and the initial temperature is 250 degree Kelvin. Nitrogen is now compressed slowly according to the polytropic relation. So now what's going to happen? This is compressed, so we go to state 2. So what do we know? If it's compressed, that means V2 should be lower than V1 according to the polytropic relation. So throughout this process here, we're going to do this following the polytropic relation. PV to the 1.4 equal to C until it reaches a final temperature of 450 degree Kelvin. Okay, so here I don't know if we need it or not, but you can say we don't know this. And then what do we need to calculate? Determine the work during the process. So what is the work done during this process? Okay, now Johnny move to step 1. So here what I would do is that I would kind of do the same figure over here. For the piston, but what's important here is to recognize that this problem is a closed system problem. Closed system basically means when the mass within the system is constant, okay, and there is no flowing mass. So for our closed system, and then we need to find the work, and we know we have the pressure. So the general equation for the work is plus minus PdV, depending on the equation you use for the first principle of thermodynamics. So let's say in this case, we're going to use the convention we are using is the Q minus work equals to change in energy. In that case, we need to use a positive one. All right, so this is the main equation. And so then we can go to basically, so it will be almost step 2. So step 1, the figure, step 2, the equation. And now, what do we know about the problem? So we know that equation, and we know that PV, let me say the N equal 1.4, over here will be equal to a constant. So from that equation, we find that the pressure is equal to the constant divided by V sub N. So if you substitute into this equation, you find out that the work would be equal to C dV OV over V to the power n. So now you can either go to the page that I gave you with the summary of all the results, but let me just redo the derivation very quick. So you know you can rewrite this as C V minus n dV, so that now the integral of this will be equal to what? C. Then you will have here V to the minus n plus 1 divided to 1 minus n. And we are integrating this between V1 and V2. So at the end, I will give you that the work equal to C1 minus n equal to V2 to the minus n plus 1 minus V1 to the minus n plus 1. Okay, so now if you remember, but otherwise the trick over here is to move the C to each one of the terms. And to do what? If you see here the equation, PV to the n equal to C. So that means what? That C can either be equal to P1 V1 to the n or to P2 V2 to the n. So we substitute over here by P2 V2 to the n, and here by P1 V1 to the n. And here you can see that this minus n will cancel with this term over here, and this one with this one. You will get that the work equal to 1 minus n P2 V2 minus P1 V1. Okay? So now I will stop over here and I will say, am I able to solve over here? Do I have all the information that I need? So let's try to find out. So in this problem, n is 1.4. We know that. Do we know P1? Yes, is 100 pascals. But we don't know P2 V2 or V1. Okay, but let's try to find P2 right away. So basically we need to go to step 3. Okay, so we need to find additional equations. Let's first try to solve then for P2. So what do we know? This is a polytropic process. So we could use P1 V1 to the n will be equal to P2 V2 to the n. Okay, so this equation doesn't look like it's enough, but then what do we know? We know that we are dealing with nitrogen. So nitrogen is an ideal gas. So what we could do is combine this equation with the ideal gas relation, and basically we'll get the polytropic relation for the gas constants but I just noticed over here that actually this problem might just be easier by just using the ideal gas relation, because you see that PV equal to nRT, and we actually know T1 and T2. All right, so let's say substituting our one equation Latin 1 into the W expression will give us what? Equal to 1 minus n, and now this become what? N R T2 minus N R T1. Okay, and this is, you see, one of these problems that I don't like why in your textbook, which is the Zengel, they use N for the gas constant, because now you can get confused about this N and this N. What is really the meaning of this N over here? So let's call this one N bar, N bar. So this is our gas constant, but this N over here is the number of moles, which basically is equal to the mass divided by the molar mass of the substance. Okay, so here you see that notation can get confusing. All right, so now we should be able to go and solve, because let's see, we have everything. So in this problem, we know that, let me just rewrite it differently, will be equal to N bar R bar 1 minus N T2 minus T1. Okay. Where over here we know that T1 is 250, T2 is 450. This N over here, the gas constant, is 1.4, and now the R bar, okay, like I told you, you should have that page over here, or a similar page. This one is from Zengel. I'll be using the tables from Zengel. Basically, if you look at this table, it's a little bit small. Let's see, we have the gas constant is at the back. The universal gas constant is equal to 8.314. So I'm going to simplify it, 8.314 kilojoules per kilomole Kelvin. Okay, and then the N bar over here, we say, well, will be the number of moles, which is equal to the mass divided by the molar mass. So now you will go to metric units. You need to go to table A1 on page 882, and for nitrogen you have that N. I'm going to round it off to 28, so but you have that M for the nitrogen is equal to 28. I round it off, kilogram per kilomole. Okay, so basically you have this N will be equal to 5 kilograms divided by 28 kilograms kilomoles. All right, so basically we have all the information we need, so we can go to step 4, which is to solve. So here we're going to have that the work will be equal to what? So here you see the units we work out perfectly. Let's maybe write them down. That would be 5 kilojoules. I'm doing the N divided by 28 kilograms kilomole. Now I'm going to multiply by the R, which is 8.314 kilojoules per kilomole Kelvin. Okay. The 1 minus N would be 1 minus 1.4. And now we have over here 450 minus 250. And this should be in Kelvin. Okay, so you will see that this kilomole will cancel with this kilomole, this kilogram with this kilogram, and this Kelvin with this Kelvin. At the end, we only left over with kilojoules. So let me pause for a second the video as I do the calculation in my calculator. Okay, so after plugging the numbers, you find out that it's equal to minus 742 kilojoules. Okay, so is that work done by the system or is work done on the system? So remember, we use this sign convention. So for that sign convention, if this is our system, we know Q will be positive, negative, and now work coming out is positive, and work out, and work in is negative. So if you remember, this will be positive, this will be negative. So basically, if the value is negative, that means that it's work done on the system. And that makes sense, because if you want to compress your gas over here, what you need to do is to push on the piston. So that means you need to apply work on the system. Okay, thank you for your time.